And for me, I think the most difficult thing is that I always have to pick a different song that is kind of like related to the lecture today. And sometimes like today, I really ran out of idea. Then it turns out that it's always like Katy Perry pop-ups in my mind. So, if one day you hear that I play a song before Katy Perry, a Katy Perry song before the lecture, it must be because of that. But well, the reason is because we are talking about very important topics today. So we are going to talk about multi-threaded hardware and the issue of programming on multi-threaded hardware. And like every processor that we are using right now, no matter how big or how small your computer is typically a multi-core processor or multi-threaded processor in different ways. How we exploit the thread level parallelism. So it's very important that you know what the underlying architecture looks like and how to program them correctly. So, but before that, right, it's always a good idea for us to start with where we are coming from. So this is where we are coming from. So every processor we have right now is pretty much like this. So this is the 12th generation Intel Alder Lake processor, exactly the same machine that you guys have been using for your assignments as well as your lab. So in this kind of processor, you have a 5-issue ALU pipeline, 7-issue memory pipeline. No matter how many issue it is, one important message I want to let you know is that these processors, they have the capability to execute multiple instructions at the same time. And if you program them carefully, the best thing you could do is that you can potentially execute 12 instructions concurrently. However, if you summarize all the characteristics, and Intel Alder Lake is not the only processor with that kind of characteristics. So most modern processors, they all have this kind of characteristics. They have multi-issue pipeline, which means that they have multiple ALUs, multiple load store units, and they have a dynamic out-of-order scheduling unit to reorder instructions whenever it's possible or appropriate. And we also have cache, which has pretty high hit rate. So most of the time, your instruction cache should not have any miss because instruction has very good locality, right? Most of the time, if your data is in an array, the miss rate should be pretty low, right? So that's why the idea of lookup table that we visit in the last lecture will work out. And we also have pretty good branch predictors as long as your code is predictable. However, if you remember the code demo we had, right? If today you use like a switch statement to implement the case that to implement some of the logic operations, then it turns out that the control flow in your logic, then turns out this switch is very hard to judge because it is spread out and there's no way we can predict what's going to happen. However, if you look at like code D, right, this I smaller than 16 is so obvious, even the compiler know that every time you are going to do it for 16 times. So even without the program's processor's assistance, we can still able to unroll this to get the performance we want, right? So that's and within this code pieces of a code, we also see, right, the power of lookup table. But again, if you don't have a cache, then this idea won't work out because this is going to be a very, very long operation. So a lot of stuff, a lot of code optimization, they cannot alive because they cannot become alive without those architectural optimization. And needless to say, the fastest version to solve the same problem is indeed you can just use one instruction in x86 to solve this issue, and you will get like twice speed up over the best human programmable version, right? So that's what and to go from here to here, that's not an obvious work that a compiler can do. So that's why as a programmer, you have to be always aware what are the new additions in your processor. So one of the new additions that we are going to talk about is probably the parallel architecture today. But before we going in there, there is one summary slide that I think that will be pretty helpful for the rest of your life. So like, seriously, right? Like how can we like program modern processors correctly, right? Or efficiently? So there are a few things, right? So minimize critical path operations, right? So for example, through the data dependency graph analysis, you know like some of the operations like memory, they are terribly long, right? And your code is pretty much controlled by the time you execute those, right? So if you have a data dependency chain that completely relies on memory operations, one of the very good example is linked list traversal, right? Then no matter how many other instructions you add in between each memory operation, it doesn't affect the performance, right? So one thing that you can imagine, right? If today linked list traversal is something that I really cannot avoid, can I insert as many other operations together with those linked list traversal, right? So that's a way to optimize performance, right? Or again, right, on the other hand, you can always thinking about if there is a way we can minimize this critical path operation. So for example, branch could take a lot of time, right? But as we mentioned, for those branch instructions, we can avoid them, right? So one good example is that we can avoid them through use lookup tables, right? We can avoid them through loop unrolling, right? So a lot of stuff you can actually avoid the branch. Or if the branch is unavoidable, can I have some way making the branch itself becomes more predictable? So for example, we sorted the data, right? That's why we got good performance after we invoke the sorting before query, right? Or there are also some low latency operations. So one of the things that you notice that I try to use AND instead of mod for some numbers, right? Because if you want to do mod, in many cases, it's probably a very time-consuming operation, right? You need a division and you need a subtraction, right? So mod is not a very easy to do operation. So if you can avoid that kind of stuff by using other stuff, and in fact, nowadays, smart compilers, they can try to figure out, okay, so another thing, if you mod an integer, right? Smart compiler could figure out what's the right way to interpret and avoid that mod, right? But if your code is not in that way, right, then your compiler cannot do anything. So some of you might say, well, for this, can compiler do anything with it? The answer is yes, but only if you give compiler sufficient amount of hints, like you specifically tell the compiler what's the number or what's the multiplication of that number.
I was wondering how many compiler optimizations really, I guess, apply to like Java or Python, or did they do like loop unrolling? Or can Python even do that with?
Good question. So Python, by default, they don't do loop unrolling. But here's the but. So right now, Python also, because people rely on Python a lot, but people also hate the fact that Python has very bad performance. So there is some, so there is one side of research called just-in-time compiler. So what happened in a just-in-time compiler is that when you are interpreting it, we keep monitoring the behavior of your code. And if we find like this part of the code is always stable as what it is, we could avoid the recompilation process. And through that process, we can also try to do some kind of optimization in your code. And for Java, I believe they also have a lot of optimizations like that. And in fact, before Python were the mainstream, Java was also one of the most intensively investigated runtime in the world. So I have been attending some of the programming language conference 10 years ago. Everyone is talking about how we optimize Java, right? But as you know, right, even though researcher has done a lot, how do you feel the Java performance nowadays, right? I mean, I don't want to tell you too much about it, but there's a limitation what human beings can do, right? And if that problem can be really solved well, right, I think C will be dead, right? But C is still long standing, right? There's a reason for that, right? Okay. Okay, another thing, right? Since processor has multiple functional units, so your code must be able to exploit the instruction level parallelism. So remember, starting from today, we are going to talk many types of parallelism. So instruction level parallelism means the ability to execute instructions from the same running instance concurrently. So if it's a single running program instance for which refer to the abstraction of process in modern operating system, then if you are able to exploit that kind of parallelism among instructions, then it's called instruction level parallelism. And given the techniques that we've learned, like superscalar or out-of-order execution plus register renaming, we are pretty much making use of multiple ALUs to achieve instruction level parallelism. And don't forget about that, right? So as I said, right, if you really cannot shorten your critical path, can we hide more instructions in parallel with those memory operations, right? Okay, so if I cannot avoid this 4 cycle delays in each memory operations, and thinking about like if I have 20 instructions that I can insert, then I can pretty much hide this 20 instructions inside, but along with this 4 cycles. Or can we have multiple memory operations running together, right? And if they are not conflict with each other. So for example, if today I'm doing tree search, right? Can I have multiple tree search happening at the same time, right? Multiple like paths of tree search happening at the same time. No, I'm just giving a random idea. I don't know if it's possible. Maybe, maybe not, right? And so that's a way how you can exploit instruction level parallelism. And finally, we have seen that pop count, right? We spend a lot of effort giving you 5 different versions of code, right? But none of them can beat just one line of code given by x86 intrinsics, right? So if hardware supports that instruction, come on, use it, right? Use it, right? If hardware supports that, why don't you just use it, right? Why do you so, eager on the algorithm, your intelligent algorithm that you implemented, right? So a lot of people saying that, okay, I have a very low complexity algorithm, even better than like matrix multiplication. That's a very good example, right? A lot of people saying that I can do matrix multiplication in order n to the 2.7, for example, right? Because the standard one is over order n cubical. However, even though it's n cubical, but if that n cubical is accelerated by the hardware, even though you implement this n to 2.7, that doesn't matter because it's not going to be faster anyway. And if it's not faster, why are we using it, right? So that's one thing that you really need to know. Like, okay, don't reinvent a wheel if the wheel is already better than yours, right? Why do you do it, right? So finally, right? Compilers don't over rely on it. So there are things the compiler can do, but there are also things the compiler cannot do. So for example, like the 5th version the version D in pop counts, right? It's obviously a pop count problem, but the compiler just cannot figure it out because it's not that obvious to the compiler, right? So those are the stuff that compiler are limited. And for pop counts, right, here's a summary, right? As you can see, so we find there are quite a few interesting things, right? So if you look at the execution time, the one instruction implementation is definitely going to give you the shortest, smallest amount of instruction count. But if you look at the ILP or say the CPI, right, it's definitely not the best. So that's why performance equation is so important because instruction count doesn't mean everything. CPI doesn't mean everything, right? And I didn't list cycle time because all of them are running on the same processor. So the cycle time is essentially the same. But this is also a good example why instruction count itself doesn't mean anything. Why CPI itself doesn't mean anything, right? And if you think about flops, it's pretty much another way of interpreting CPI, right? It's just a floating point CPI, to be honest, right? So for that case, right, that's why flops doesn't reflect anything. And the best one, right, like B, it has 4.5 IPC, right? Or say pretty much like a 0.2 something CPI. But what about performance? It's even not the best. It's not the best, not the second best, not the third best, right? And for the best performing one, only have 2.7. But another thing that you want to notice, right? Remember, this is a processor with 5 issues, right? And if we want to go with the best implementation, it's probably this one. But what about its CPI or IPC, right? 2.7 simply means most of the time we are going to use smaller than 3, fewer than 3 functional units. And thinking about and this is on the Elder Lake processor that I show you, right? So most of the time, at least 2 of them are idle, right? So, and there are many cases we cannot avoid code like linked list, right? So if you look at linked list, the IPC or say the CPI is really bad, or say the IOP is really bad, right? And we are wasting a lot of resource there, right? So what's the best to do, right? So saying that if San Diego built a private park that only 1 or 2 people can visit, isn't that a waste, right? Why shouldn't we like open up to the public, right? So same thing, right? So if you look at like, okay, even for this piece of code seems to be a very good performing one, but we still wasted a lot of cycles that we cannot issue any instruction. So whenever you cannot issue instruction at a cycle, you are wasting your hardware resource. So to avoid this hardware resource, there are many hardware optimizations and software optimization that we can do. So today we are going to talk about that. So the very first one that I'm going to talk about is simultaneous multi-threading. So this photo is actually 10 years ago that I took at UC San Diego. I think it is 3109, the conference room. And that was actually my PhD defense. And that's me. And this guy is called Dean Townsend. This guy is called Steven Swanson. They are both still in UCSC CSE. But why am I showing this up? Because my advisor, Dean Townsend, was actually the inventor of simultaneous multi-threading. And simultaneous multi-threading, it has a trademark called hyper-threading by Intel. So what is simultaneous multi-threading, or say hyper-threading? So it leverages the concept that we said, right? If we have a lot of good facilities and if it's underutilized, why can't we share it others, right? So, so for example, like UCSD has pretty good facilities, right? And we do share with the community for REMAC, right? How many of you go to the gym regularly? Yeah, but if we share with the community, right? And plus there are not that many people living here around, right? So we share the community. We don't hurt a lot, but others would be happier too, right? So that's the idea of simultaneous multi-threading, which means that, okay, we try to extend the processor so that the processor, even though we don't add more functional units in a pipeline, we can allow another running program instance to share the facilities, main facilities provided by the processor. So that, which means that, okay, now I want to extend the processor in a way that I can fetch instructions from different threads or process to fill the pipeline. So in this way, you can thinking about this processor now, it has the capability to execute multiple threads at the same time, instructions from multiple threads at the same time. So you are actually using a single processor to improve the thread level parallelism. So, so here's the idea, right? So that's the original execution flow. So we see a lot of wasted slots, right? So what we are thinking is that, okay, we invite another program, which is the purple one on the right-hand side. And what we can do is that, okay, we still give one of the process higher priority because that's the original one. Like, okay, when we are using REMAC, right? So maybe we should give UCSD students higher priority, although most of the time I think we are giving students lower priority, right? Whenever there's a special event, you get kicked out. But anyway, supposedly you are giving people you give some priority to the original program, and then whenever there is a wasted slot, like here, right, we can schedule, we can again fetch these instructions, have them in a queue, and fill the wasted slots with instructions from another thread, so that every wasted issue slot can be filled with an instruction that is not from the same program at the same time, right? So what you have to do is that, okay, how can I get two programs onto the same processor, right? So a few things, right? If you want to track two processors, the progress of two running instances, you need two program counters, for example, right? So which means that, okay, I need a different program counter for each running instance on the processor. And the other thing is that everyone has an RAX, everyone has an EAX, EBX, ECX, right? So you need a different mapping table for your register renaming, right? So those are the things that are necessary, right? Other than that, for physical registers, right? Since they are originally virtual registers, so as long as the mapping works and since we are underutilized, I don't believe we are fully utilize those physical registers. So we probably don't need to have more physical register than we already have, right? For cache, yeah, you can definitely make it large, but is it necessary, right? Maybe it's not 100% necessary, right? And even though without increase the size of your cache, and don't forget, right, we already have the virtual index physically tag the cache. So you have a mechanism to avoid aliasing or confusion in your virtual addresses. So you don't actually need any hardware extension to support two threads on the same pieces of cache, right? And functional units, we don't want to duplicate it because the whole purpose of this simultaneous multi-threaded design is we want to share, right? And finally, duplicated reorder buffer. You probably want or not, right? Because all you need to do is that I can distinguish the instruction in a queue is from which process, then I'm done, right? So as long as the reorder buffer, like your execution progress, is not stacked in a way that is affecting the decoding of incoming instructions, you are good, right? So it seems like, okay, we only need to have two physical registers, two program counters, which is just another register. Isn't that hard? Is that hard? No, it's not, right? We only need a new architectural register. Is that hard? That's not hard, right? So the good deal is that, well, at the time that the paper is published or the idea is published, their claim is that, well, for a superscalar processor, you only need 6% more area to support simultaneous multi-threading. So that's a pretty good deal, right? Like with 6% area increase, you can have one more thread sharing your pipeline. So here's the idea, right? So simultaneous multi-threading is essentially another version of superscalar register renaming pipeline, except we have, compare the difference, right? We have one more program counter, and you probably need to have a smarter register renaming logic and register renaming table to support two sets of your program. But other than that, you're done, right? Very simple extension. And so now the second question is that how can we have two programs running concurrently? So definitely you need to cheat your operating system, right? Yeah, I hate the word cheating, right? Like sometimes, yeah, I don't want to say that. That's politically incorrect. I was about to say that, right? You only have one person, but can you date together with two person and pretend you are single, right? But yeah, here's the thing, right? It's pretty much like this. So this processor, it tells the operating system in a way that by exposing two program counters and exposing two core IDs, right? So then it gives the operating system an illusion. Oh, I got two processors, right? And if the operating system sees two processors, then it will schedule two programs. For example, like a number or a numbers instance or a Chrome instance, right? And both of them, operating system would misunderstood the fact that we have two processors and schedule them all together, although they have different front end. For example, like on the dating profile, I can call myself Nancy. I can also call myself Wesley, even though it's different sex identity, right? But I can still like, treat it with others. So same thing, the processor is exactly doing the same thing. So, like computer hardware, they are designed by human beings. So we try to observe how human beings fully utilize their resource, right? And sometimes, yeah, it's a bad joke, right? So sometimes we have friends, they have long distance with people who are on different time zone, right? And we sometimes joke with them. You can technically have a girlfriend during the evening and another one during the daytime. All right, don't file me on anything like that, right? But what I'm going to say is that the hardware creates an illusion that the processor is a dual core processor, so that the operating system will be cheated. See, it's pretty much like the real life. Okay, I don't want to say too much about it, right? The operating system is cheated. So the operating system will schedule two process or two running instances on different core ID with different PC, but physically they are on the same processor pipeline. So that's the trick that simultaneous multi-threading is playing, right? How evil is it, right? So, okay, with this trick, right? Well, no matter how you think about this, right? Can you imagine this processor's pros and cons? Yes.
I was thinking that there's only one program counter register in hardware, right? That holds the address, the program counter, and then on a context switch.
On a context switch, you are going to give it a program counter differently. But because the program counter, when you have a context switch, you are going to also reprogram your virtual to physical memory mapping table, right? So even though it's the same PC, it will be referred to different physical address.
Totally. Okay, but so there's only one PC register in hardware, right? Or is there
By default, but simultaneous multi-threading is making them two or more.
in hardware?
Yes.
Oh, okay.
So that's how the operating system got cheated. And that's why you still have 6% of the overhead. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looking at the first run, we have a pretty high approval rate of the answer C. So why don't we just look at, okay, what are the two that you guys have in mind that is correct or that are correct? What are the two? 2 and 4. 3 and 4. You just choose 4. 3 and 4. Okay, I think it's a better idea that we should go into discussion. Okay, now you know that even though it's C, right? Everybody's C is different from the other. So go discuss.
3 and 4.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, after discussion, oh, more of you think it's C, but you know, there are 3 and 4 and 2 and 4. What do you guys think after the discussion? 3 and 4? How many of you are 3 and 4? Okay, 2 and 4. Okay, slightly more. So none of you agree with 1. Why? So SMT makes processors with deep pipelines more tolerable to mispredicted branches. True or false?
Like it wouldn't have an effect. But it's really, so deep pipelines means like many stages, right?
Right. So an evidence of deep pipelining is like, okay, right now you see in the last demo, right? One of the last 2 demos that I show is that whenever there's a branch miss, right, it's 34 cycles, right? Which means that you have at least 34 pipeline stages, right? Can you imagine that I ask you to write Verilog with 34 stages of pipelines? Okay, right, I see your face, right? So isn't that deep enough, right? So how does that related to mispredicted branches? So what can you do with SMT, or what you can do without SMT? It's the same thing, actually. English is hard. What are you going to do in general?
Utilize more of the CPU.
Like, if you don't have SMT, what will your processor do? And why are we seeing 34 cycles delay? What? Okay, so what happened, right? It's pretty much, so that's why in companies, okay, I don't know how many of you are having experience in doing research, right? But like if you do research here, typically professor would give you like a weekly meeting, right? So what would typically happen is that, okay, that's why I'm saying that humans' memory are limited. And I always want my student to keep a note. But even though you keep the note, you just reduce the branch misprediction rate. But always, right? There is always a case, okay, I'm done with my meeting today. I'm so happy. I'm so relaxing, right? And especially like I meet with my students on Thursdays. So, Thursdays, as I talked to you guys a long time ago, Southern California party night, right? So they have party in the evening. No, I'm just guessing. But then the next day is Friday. Do you work on Fridays? Right? Okay, you guys are honest, right? And then do you work on Saturday? Right? How about Sunday? Right? Bingo, right? On Monday, do you remember what's going on? What? So you just, so it's pretty much branch prediction now, right? I just predict what the advisor really want me to do. And then I predict that and I work on things, right? Which might not be on the right direction. And the next Thursday, my professor tells me, no, you're on the wrong direction. Right? So what does that happen? So the progress of the whole 3 days effectively should be 7 days, right? Is actually wrong. And you have to flush things out and you have to ramp up your execution again, right? That's exactly what a processor would do. If there is a branch misprediction, in the very beginning, we don't know it's misprediction, right? So we just keep working on things. And at that time, we might pollute the cache. We might waste the hardware resource working on something nonsense, right? And most of the company, what they are doing is that they do daily stand up meaning, right? So that's why we can reduce the misprediction. So they have a shorter pipeline, right, to avoid that problem, right? Okay, but if you have a very long pipeline, it's pretty much like, okay, the progress within a week is wrong, right? So here, right, pretty much like this, right? If you have a predictive pipeline and saying that if my branch prediction is put in the 33 stage or 34 stage, and that's pretty much the case in x86 processor, the branch is actually at the the second last stage of the pipeline. I don't actually know why they do it, but that's exactly how they do it. So branch is already at the very end of the pipeline. So if you have a branch misprediction, and don't forget, we have 5 issue or 12 issue pipeline. And let's say if you have 5 issue pipeline, and if you have 30 stage ahead of time, you are potentially getting 150 incorrect instructions in the reorder buffer, and you have to flush them out. And all the progress made by these 150 instructions are actually nonsense. Okay, but what can you do with SMT? If you have SMT, what can you do alternatively? You can actually fetch in. So if I have a branch, right, I am now knowing that, okay, I see a branch, I may have to do some prediction, but why don't I just give higher priority to another program, right, for instructions that makes more sense, right? So isn't that make the SMT processor more tolerable to branch misprediction? Because overall, right, the cost of misprediction is less, right? So that's why I would say the first one would be correct. How about the second one? So some of you think the second one were correct? Why not? Why or why not? Is it correct? No? Why not? What? Because it's single-threaded anyway, but are we going to improve or we are not going to improve, right? Are we going to affect the performance? Thinking about my UC San Diego remake example, are we going to affect the performance? The answer is you are going to hurt performance, right? Because you will share your resource with others, right? What if, okay, for now, I don't see there is an immediate demand that you want to use memory unit. So I lend your memory unit to another thread. But then immediately you have the request of intensive memory request. Now you have to share your resource with others, right? So it will hurt performance, to be honest, right? Whenever it's shared, right? That's why people want like exclusive VIP access to a lot of things, because it means that you have the exclusive resource of accessing anything, right? But for SMT, it's definitely hurt that property. How about the third one? Can we better utilize hardware during cache misses? Do you compare against a superscalar processor with the same issue with? You nod your head. Why?
I say yes, because now that downtime where we're waiting for the cache hit and return, we can run a different thread.
Okay, right. So one thing that I want to say, right, is again, similar to the branch prediction example. If we have a cache miss, for example, linked list, right? I know the cache miss take a lot of time to handle. Now I can give priority to another thread. And the other thread might be a compute intensive one. So both are happy, right? Your memory request is served and the other thread also make progress. How about the last one? SMT has higher cache rate compared with superscalar processor when executing the same set of applications. This is a difficult question. Is it difficult? What do you think? Mm-hmm. Okay, so even though you don't give priority to another program, right, you are sharing your cache with others anyway. And cache is already a very tight resource to a lot of programs, right? So you're definitely going to get some performance hit because you are sharing the cache, right? Okay, so I would say three of them are, oh, yeah, three of them are actually correct. 1, 3, and 4, right? So yeah, I know this is a question that you really need to think through. Okay, so but overall, right, going through this question, you can think SMT is a good way to execute to improve the throughput of execution. When we say throughput, it's the throughput of all programs, not a throughput of a single program, because it's going to hurt the throughput of a single program, right? And it make the branch misprediction penalty fewer per thread on average. Again, right? Maybe it doesn't affect each if you only have one thread, but if you're running many of them together, on average, each one will be better, making the hardware utilization higher so we don't waste idle power. And the hardware design is simple, right? As we tell you, you only need to duplicate the PC and register files. And in fact, in many architectures, like Intel start with their hyper-threading. And because it was registered by Intel and it was patent, so the patent has like 15 years that others cannot implement that. So even though it's a good idea, AMD finally adopt that design 15 years later when it comes to the Zen microarchitecture, right? So right now, because of the patent pretty much expired, so all processors, they probably all have the simultaneous multi-threading design, even though we see some disadvantage of that, but it's everywhere. Okay, and the guy invented that is actually in UC San Diego, so if you're interested, you can talk to him. And right now, if you do LSCPU, right, which you can do in our QB Hub machine or any of machine that running Linux, and if you have a Windows, don't be too sad. You can also use CPU ID or CPU Z, right? That will tell you the detail of your processor. If you see like 2 threads per core, right? That pretty much that means that you have simultaneous multi-threading. But then sooner you will notice that my processor also have another line calling that I have 4 cores per socket. What does that mean? So it actually is the second idea that we are going to talk about today, chip multiprocessor, or say multi-core processors. So let's go back from this one, right? So this is probably one also, well, so for in my class, like von Neumann architecture is the most frequently shown one, right? But Moore's law is probably the one that a lot of hardware-oriented architecture class will show. So don't forget, right? Moore's law is important because it shows that we have no trouble of putting more transistors within the same die area, right? So now, if you're the company, if you are allowed to put more transistors, what are your options? So here are the data. Well, so this morning, we know every day I'm doing course preparation, and every time I'm very unsatisfied with my slides. So even this morning, I'm doing some incremental improvement, and I was trying to find data regarding how many transistors are there in each processor. And originally, I based on this context, but turns out you have to do a lot of calculations. So it was 10 minutes before the lecture, so that's why I started to ask Bart, okay, how many transistor per core on Coffee Lake? And actually, I made, and those Lake bridge, the Nihelion, those are the Intel microarchitecture code names. So you know, different companies, they have different ways. And AMD is one of the company with a lot of code names. Like each project, they have code name, they have bigger architecture name or something. So they have a lot of complex code names. But for Intel, it's pretty much like the name of some place, right? Nihelion, I think it's a city in Oregon. I don't know where Sandy Bridge, Coffee Lake, and Elder Lakes are, but they are they are indeed real places. Okay, so according to Bart, if it's wrong, don't blame me, blame Bart. And the reason why I have to ask Bart or try to look out for this information so difficult because Intel consider the number of transistor count on their processor as a top secret. So they never tell you what exactly how much each core, how many transistors each core would use. So they only tell you the total number of transistors that we have in the processor. So that's why when I draw this Moore's law, I can get the density of the chip because in that way, they can show you how good our process technology is. But they don't want to tell you how many more transistors we put in each generation of the processor because they don't want you to know or guess what innovations we have done on our processor. So I can only roughly guess it or calculate it by some rough numbers. But from this table, right, you can see the latest generation of is actually right now it's called Raptor Lake, but Raptor Lake is actually a tweak. Intel has the TikTok, right? So it is actually the talk for Elder Lake. So it's essentially the same as Elder Lake processor. So for the Elder Lake processor, we have about 3.5 millions. 325 millions of transistors, and with 3.25 millions of transistors, you can build 5-issue LU pipeline plus 7-issue memory pipeline. And 2008, with half amount of the transistors, you are able to have a processor with 3 times LUs, right? So right now is that, okay, if you are given the same number, if you have the transistor count to build a Elder Lake processor, which give you 5-issue LUs, or do you want to have 2 cores that runs Nihilium, and each is a 6-issue processor, which give you 2 times 3-issue LU. So effectively, you will have 6 LUs that you can share among 2 programs. Well, you can split them for 2 programs. And you also get parallelism of running 2 programs, right? And if you think about the fact, most of the time, we are not going to use about that many instruction level parallelism. Isn't that a good deal, right? So here comes the idea of chip multiprocessor is that instead of using the same area of building a joint processor, we share the last level cache, but we have more processor cores within the same die area so that I can schedule more programs concurrently. And don't forget, this time is a real processor. It's not a fake virtual processor that simultaneous multi-threading used to cheat your operating system. So the concept of CMP, right? So that's a similar one. The operating system also have a set of processes that they want to schedule. But this time, each processor only have 1 PC. And so that these 2 processors, they are physically 2 separate processors. And each of them is a very loyal one, very dedicated one. They will never cheat on you, right? And then the operating system sees that, okay, we have 2 processors and we schedule 2 processes on these 2 separate processors at the same time, right? So you can see from the operating system, the front end is pretty much the same. However, the hardware is completely different. One has a physical resource, the other one doesn't have it. Okay, so this is the concept. I want you to check these 4 statements and tell me what do you think about it. You know, when Brendan asked me the question, I was about to, at the same time, I was thinking about Brendan is going to ask me about my story of being cheated. Yeah, but you know, I don't want to say too much, but I do have an experience with long distance relationship, and you know, when we broke up, the other was with another person immediately, as far as I know. I don't know if it's a cheating, but I would say like a seamless transition. Yeah, and it was a time when I was in North Carolina and the other was in California, 3 hour distance, right? So, when someone off the work, I was pretty tired. So yeah, reasonable. Long distance relationship is hard. All right, wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay. Yeah, I like this graph. So why don't we go ahead and discuss with your friends and let's see what you guys think afterwards. 90 seconds. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, more of you think it's two. Some of you move to one. So, let's look at each, right? So if you look at the question, what I'm trying to do is that I'm trying to give you a comparable architecture in a way that if you look at SMT, right, we have we can support 4 threads, 6 issue pipeline, right? And for CMP, I'm giving you a better deal, 4 threads, and each is a 2 issue pipeline, right? So for CMP, it's pretty much like 6 ALUs concurrently. And this is pretty much like, sorry, for CMP, it's most of the time, if you do things carefully, it's 8, right? And if you have SMT, it's going to be 6 in total. Pretty similar to the Nihilian and Elder Lake comparison, right? Remember, Elder Lake has 5 ALUs, and Nihilian has 3 each, right? So I'm doing a pretty reasonable comparison at this point. So now, and in terms of the cache size, right? So for the SMT process, I give you 64 kilobytes, which is pretty generous, right? And for CMP, I have 16 kilobytes each. And given that you have 4 cores, it's 4 times 16. So effectively, it's partitioning the 64 to 4 different exclusive ones to each core, right? So, I mean, the area on the right-hand side is, to be honest, the area of the CMP is still going to be smaller. But at least in this way, you will feel it's a very similar situation. Okay, given that, if we are just running one program in the system, the program will perform better on an SMT processor. Is that true? What do you guys think? If you only have one process, no? Why not? Okay, so what's your thought again?
I don't think like if you just have like one
Mhm.
necessarily be helped by SMT processor.
But if you run it on a CMT processor, is it going to be better or worse?
Versus the CMT.
Okay, when I say better, it's compared against CMP. You think it's better? Why? You have more resources and larger cache, right? So the first one is probably pretty straightforward, right? How about the second one? If we are running 4 applications simultaneously, the cache miss rate will be higher on the SMT processor. Brendan? No, right? If you have a single program, what if saying that my IOP is pretty much like 3 point something, right? Or saying that I just need larger cache, right? So the first case, a single process would anyway enjoy more resources, all right? So, okay, so maybe the claim of strong is better, is too strong for better. At least it's not going to be worse, right? Okay, how about the second? Will the cache miss rate be higher in the SMT processor if I have 4 threads concurrently? The overall cache miss rate. What do you guys think?
I think it will because we have dedicated caches for the multi-core. So each application can run on each core and there'll be less like eviction from the caches because it's just using the stuff that's useful to that program.
Okay. Other thoughts? Do you all agree with Brandon? Leon, what's your thoughts? Right. Okay, so here's the thing, right? Okay, maybe I have 4 applications, but what if one of them has a footprint of 32 kilobytes and the other only have 8, right? So in that case, if you have CMP, right, the one with 32 kilobytes footprint can only use 16 at most, but the other ones that use only 8K, they have another 8K which is wasted, right? So that's the beauty of the SMT, right? But it also means it depends, right? As Brandon said, if everyone has more, or like if everyone and it's pretty similar, an exclusive cache would guarantee at least everyone has some resource to make progress. It won't be the case that one always kick out the other, right? So that's why you want to separate room for your kids, right? Yeah, I cannot believe UC San Diego's undergrad housing is now having like a shared room configuration between 2 of us. Can you imagine that? Like share the bedroom with another person? What? You did? How was it? You're fine. Okay, so you are the one who is good with SMT. All right. Yeah, if you guys are compatible, right? That's good, right? If you guys are not compatible, so the answer is that it depends, right? How about the third one? If we are running 4 applications simultaneously, the misprediction rate will be higher in the SMT processor.
And branch misprediction. When you context switch, like do you get the same.
What do you mean by
back.
context switch here?
Like, is the misprediction rates all of the applications kind of overlapping, or would the
Okay, the overall
it wouldn't
branch.
overlap because you're context switching back and forth? So it's like,
What do you mean by context switching?
so on like an SMT, as it runs for applications, it would kind of try to make some progress on one, and then depending on situation, context switch out, and another one context switches back in.
Are you context switch back in? Okay, so here is a, okay. It's unfortunately that I don't teach your operating system, but whenever we say context switch, no matter this is in operating system class or in architecture class, it's pretty much the behavior that we change the page table to another process. We change the program counter by restoring the program counter from a program that has been put into sleep. Do you have to do that when you are doing CMP or SMT when sharing your hardware resource?
Really depends on the schedule.
No, you don't. Because if you are having two threads running concurrently on the SMT hardware, that's why we need two different program counters, right? You don't restore these two program counters. You don't change your patch table mapping as long as this process are already in your processor. So another question which I asked in the past, right? Like, is SMT better for context switching or not? The answer is that yes, because SMT actually reduces the chances for context switching because you are within the same amount of hardware resource, you are able to reduce half of the context switch because more of your processes are now, even though they are not making progress, the context is still kept alive by the program counter and the resource of the SMT hardware. And the same thing for CMP, right? A program counter is a hardware context, right? So if you are talking about getting different instructions from two different programs in the same time, they are both from a running context. So there's not really a context switching by any means. Okay, so in this case, how about the branch misprediction rate? Although they don't have context switch, but they share the same predictor. How does that work? What? The misprediction rate will be higher? Okay, so I would say it depends. Sometimes it will be higher, sometimes it won't, right? Because again, branch predictors is trained by different ways. It could be global predictor. It could be local predictor, right? So if it's local predictor, it's actually different program counter if it's a different program. And there is also a case, right? I am running two processes or two threads from the same program. For example, if I'm launching Chrome, each tab is a process. If I'm launching Firefox, each tab is a thread. So what does that mean by the same program, different process, and different threads? So they are just having different contexts of running, but they are sharing the same set of instructions, which means that they all have the same program counter. So if I have a program that is already up and running and I launch another program instances that's a clone of that running program, if I use SMT, I also share the trend branch predictor from that running program. Isn't that makes your branch prediction performance better? Can you get it? Not really. Okay. So saying that I have one Chrome instance that I'm already running. And when I run that Chrome instance already trained the branch predictor very well, right? If you have simultaneous multi-threading, and if you happen to schedule that Chrome instance, another Chrome instance on the processor already running a Chrome instance, you directly enjoy the trend branch predictor. However, if you are on a CMP context, you might have to train the predictor again. Right? So isn't that an example how SMT would actually have better branch prediction performance? But I know your understanding, right? So if I have a global predictor, then two different programs would definitely mess up the execution, right? So the answer is also it depends. How about if we are running one program with four parallel threads? The cache miss rate will be higher in the SMT processor. It depends. Okay, you got it. How about the last one? Again, right? I would say it depends. Right? So a lot of cases, right, you can acknowledge, right? So right now, you know, just that's why I like to teach upper division class. You guys are so used to the fact that there is a standard answer to every question, right? But come on, face the reality. Most of the time, there's no standard answer to every question in your life in real practice, right? Should I sell the company? Should I keep the company? Should I be the CEO or not to be the CEO? Should I break up or not break up, right? There's no standard answer to each, right? And it's all case by case, right? And sometimes, right? Why do I have to make choice, right? Why not having both, right? So that's exactly exactly the thing that modern processors are doing. So if you check the Intel Alder Lake processor, that's why you see like we have 4 sockets and each 4 cores per socket, and each core has 2 threads, right? Because we are pretty much doing this, right? This is like another drawing of your the processor you use for your lab, right? Your processor has a less level cache that connects to different processor core, and each processor core is identical, and they are identical in a way that it's a superscalar processor, but also a simultaneous multi-threading processor. Yes? Mm-hmm. So again, right? So again, as I said, what if I'm running a thread that doesn't use the cache at all, right? Okay, so most of the time, right, we want to get both, right? And since we have more transistors, why don't we just get both? So that's exactly what modern processor would do. So if you do LSCPU nowadays, you also have a simultaneous multi-threading in each core, but also it's a multi-core processor. So this is pretty much the figure reflecting nowadays. You have core ID mapped to different program counter, and each of them would allow the operating system to schedule, and some of them would be sharing the processor. So that's the reality that we are dealing with. And if you look at the AMD Ryzen processor, it's pretty much an 8-core processor, and they have the chiplet design. Each chiplet has 4 cores, and each core has its own L2 cache and shared L3. And this, they have an interconnect that can allow this some synchronization among this split L3 cache in different triplet. But that's the AMD Ryzen processor. And for the Intel Alder Lake processor, they also have a performance core with private L2 cache with a shared L3, right? So that's pretty much the bits that we are dealing with today. So one thing, so there are so many things that are, it depends, right? In your final, you cannot just tell me why it depends. You have to tell me the specific reason that I mentioned in the class. But there's one thing we know for sure. If we don't parallelize our program, there's no way we can use our chip multiprocessors. So we are going to talk about the parallel programming. So again, right, so to exploit parallel programming, you need to break up your logic into multiple processes or multiple threads. And if you don't have the operating system concept, that's fine. If you do take the operating system class, I don't believe you remember it. If you do, that will be great. But if you don't, let's recap on it. So the basic idea of parallel programming nowadays is that you can use different abstractions from your operating system. And there are two common abstractions. One is the process abstraction, and the other is a thread abstraction. And for process abstraction in the operating system, they will have separate virtual memory space for each one. And because of the separation of virtual memory space, processes, they are not allowed to talk with each other through the virtual memory abstraction. So if you are using a process abstraction to break up your computation, you have to use MPI, message passing interface, or the most naive way, which is by default what the Unix is using, is that you use file to perform message exchange or data synchronization, right? So that's a way of parallelizing your computation. And what you can do with process is that, okay, I have a big input file and everyone is taking different parts of the input file as my input. And when I output to different parts of the output file, right? So that's a way of doing it. And it's pretty much used by a lot of scientific computation, especially if you have thousands of nodes, right? You can imagine that's a very good way of parallelizing, because most of the time you take your data, you don't talk to others, and when you're done, put the stuff back, right? So you can, you pretty much can avoid the communication synchronization overhead when you have thousands of instances. And the other way is doing threads. So threads is an abstraction supported by recent operating system in a way that under the abstraction of the process, and the process is a running program, you can actually spawn a few threads, and each thread is essentially an invocation of a function within the same program. And these threads, they have a shared virtual address space that's visible to each other. So one can directly see another. One thread can directly see another without the addition of message passing. So that's the thread abstraction. So however, when we talk about the hardware architecture, like simultaneous multi-threading, like multi-threaded hardware, when we refer to thread, it's typically both of those are called a thread, because by default, there is not too much difference from the architectural perspective, because each thread, they can also have different progress. So you need a program counter to map to the thread progress anyway. For the process, is also the difference of the program counter, right? The only thing that makes difference, which is irrelevant to the processor itself, is the virtual memory space abstraction. And that's actually an artificial abstraction created by the operating system. So from the hardware side, it's all about threads. Okay, so that's the hardware side. But as I described, you can hear, okay, the software might be thinking differently from the hardware's perspective. So this is what the software is thinking about the multi-programming hardware. So the software will think, okay, this is the hardware. We have different cores, and each different cores is a vehicle that we can run a part of the computation. And they have a shared memory abstraction that we can leverage. Like all the memory, they are visible to each, they could be visible to each other. So that's what they saw, right? So what we do is that, okay, we map the shared memory as the shared virtual address space. For example, if we are doing thread programming, and if I have a program like Firefox, and this is indeed Firefox did. So Firefox actually is a multi-threaded programming model. Every tab is a separate thread. So I map each thread to a processor core, right? And some of them may be SMT, some of them maybe not, but that's set aside. And let's say it's a CMT case. So this is what the software saw. But what's wrong with it? What's missing there? What?
The cat.
Yes, exactly, right? They forgot the fact that each one has a private cache. And you might wonder, how does that bother, right? So let me give you an example. So saying that, okay, right now I have different pieces of code. One is running this for loop, starting from I0 to size to a quarter. And then this is starting from the first quarter to the second quarter. This is performing the third quarter, and this is performing the last quarter of my loop. And I want to calculate the sum of the matches, the whole array, right? This is a very simple, naive, but reasonable implementation, right? But look at this. With this kind of dangerous assumption, what's going to happen? So initially, I have sum equal to 0 in my shared virtual address space, and I load it into my L1 cache. And in the meantime, because we want parallelism, right? So another thread would definitely launch at the same time. We also get sum equal to 0, right? Okay, so now I load this sum and I modify it, saying that, okay, if the first thread makes some progress, modify my sum to be that big, right? Okay, so now others won't be able to see that updated sum. And I'm still assuming that my sum is still 0, right? So is that going to work? It's not going to work, right? So effectively in your hardware, you need to support two different types of protocol. The first one is called coherency, and the other one is called consistency. And there is a huge distinction between coherence. So coherency is about if the processor want a value, and at this time, every processor who wants value will see the same value for a certain memory location. So consistency simply means that, okay, so saying that, I don't know how you know, okay, I hate this Asian parents example, but hopefully that won't be offensive to everyone. So, you know, Asian parents, they are sometimes annoying in a way that they really care about you, or sometimes I would interpret that as some kind of a control, the desire of control, right? So if you are home too late, right, they will definitely call every of your friends, right? You are laughing, do you have that experience? Okay, yes, right. They will call every of your friends. Hey, Leon, do you see Hongwei? Where is he? Right? Like, or say, Brandon, did you see Hongwei? Where is he? Right? So what I will do, right? I will call all potential friends that I think my parents would call, saying that, hey, saying that I'm at the library, saying that I'm at the library, right? So then when your parents knowing that, okay, my son is gone for a while, right? Then, Leon, where's Hongwei? Where's Hongwei? No, you have to say library. Okay. Assume you say library, right? That's called coherent, right? But when I tell him I am in the library, or when I tell him I'm in the library, that's a different time, right? So it doesn't really matter when did you let others know you are in the library or you update the value. It's just a matter when somebody make a call asking, where is Hongwei? Everybody will say it's library. That's called coherent. Okay? It's a little bit abstracted, but it actually means that if at the same time, everyone has the same answer, that's coherent. And for consistent, it means that everyone would see the same order of updates. Everyone would agree the same order of updates. So for example, if today your parents asking about, okay, did he eat first or go to the library and eat? Right? That's a very detailed question, right? Then someone will say, okay, I know he's at the library. He probably eat after the library. And Leon probably say, oh, he ate first, right? So there's inconsistency in a story, right? So the consistency is that everyone would agree Hongwei will eat first and go to the library, right? Everyone would agree with that order. So that's consistency. So You might think, okay, how does that affect my programming? And how does that affect the program execution? That's actually a topic that we will talk about in the next Tuesday. And the reason why I say next Tuesday is because next Monday is a holiday. So enjoy your holiday. Other than that, I will see you later in the lab lecture or next Tuesday.